Hello and welcome back to Functions. First, I want to thank all the nice people that support this channel by liking and subscribing. In today's part 4, I'd like to continue with rational functions, but a bit more difficult ones, and also show a special case. So, let's begin first with an example. We have a rational function given by f of x equals to 3x squared minus 12 divided by x squared plus 3x minus 4. Let's try to sketch this. This means that we need to identify several things. First, we need to find any asymptotes that includes horizontal and vertical. Preferably, we can also find x and y intercepts if they do exist, and then we can confirm the domain and range so that we can graph the function correctly. So, just like before, let's first begin with our domain, which will give us the vertical asymptote. We have a denominator, which is given by x squared plus 3x minus 4. Now we know that this can't be equal to 0. So technically, let's just solve this equal to 0. It's just a quadratic function. We can solve this using factorization. It's given by x minus 1 times x plus 4. So that means x can be equal to 1 and x can be equal to negative 4. These two values here, 1 and negative 4, are going to be our vertical asymptotes. And don't be surprised, there can be more than one vertical asymptote, just like you see here. However, of course, you might wonder how the graph is going to look like, which we'll get to soon. So, that means the domain for this function is just going to be x does not equal to 1 and does not equal to negative 4. Now, let's move on to the range. What we can do here is take the limit as x approaches infinity, or to be more precise, plus minus infinity of our rational function. If you do the limit by yourself, what you're going to get is that it's equal to 3. So that means when y is equal to 3, what we're going to have is a horizontal asymptote. This also means that y just doesn't equal to 3. However, there is actually a hack to finding horizontal asymptotes. Suppose we have a rational function and we now look at the powers of our numerator and denominator. What we're going to have are three different cases. The first one is that the power of the polynomial in the denominator is greater than the power of the polynomial in the numerator. Very simple example would be y is equal to, let's say, x plus 3 divided by x squared plus 3x minus 5. In the numerator, we have a linear function, so that's power of 1. In the denominator, we have a quadratic function, which is power of 2. In this case, the horizontal asymptote is always going to be 0. So horizontal asymptote automatically will be y equals to 0. Now, in the second case, you might have guessed, what if the powers are the same? Just like in our example, both the numerator and the denominator's polynomials are squared, are quadratic. So that means they have the same power. The horizontal asymptote here is simply going to be the division of their leading coefficient. On the top here, we have 3x squared minus 12. The leading coefficient is going to be 3. On the bottom, we have x squared plus 3x minus 4. The leading coefficient, even though it's not written, it's just 1. So that means the horizontal asymptote is going to be equal to 3 divided by 1, which is simply 3. Same answer we got using the limit. Now, the very last case, the third one, is going to be that the power of the polynomial in the denominator is actually less than the one in the numerator. So we take that same example as the first one, or we're just going to flip it. We're going to write as x squared plus 3x minus 5 divided by x plus 3. What happens here? Here, we won't have a horizontal asymptote. This is more of a little special case, and we're going to have a different kind of asymptote, which I will definitely come back to later. However, for now, let's just continue with the example that we are solving. Okay. So now that we have the two vertical asymptotes and the one horizontal asymptote, the next thing we can find perhaps are the x and y intercepts. X-intercepts are quite easy to find. What you do is that you equate our function to 0. However, for a rational function to be equal to 0, all you do is take the numerator and you equate it to 0. So we're basically solving the upper quadratic function. What we get is 2 and 0 and negative 2 and 0. For the y-intercept, it actually is even easier, because all we have to do is plug in x equals to 0 into our function. So what we get is negative 12 divided by negative 4, which means we get 3. So 0 and 3 is going to be our y-intercept. So now that we have all this information, let's plot it on a graph. Okay, now that we have plotted everything on the plane, some of you might notice a slight problem. How can we have an x equals to 0 and y equals to 3, so that means an intercept here, but at the same time we also have a horizontal asymptote at y equals to 3. Now here comes the problem. It's a common misconception of the asymptotes. Horizontal asymptote is just the value that the function approaches as x becomes bigger and bigger. Here, since we have two asymptotes, that means that our function is going to be a part of the function that's simply going to exist between these two asymptotes, between negative 4 and 1. That means inside here, in this part, in this compartment, our graph never approaches plus or minus infinity. At least the x value of it will never approach plus minus infinity. Hence, that means this portion of the graph is allowed to cross the horizontal asymptote. And our function is going to look something like this. Definitely a little bit interesting and a little bit weird. Unfortunately, for you guys, there is another form which these more complex rational functions can possess. So let's take a look at another example. We have a function here, rational one, 2x plus 8 divided by x squared minus x minus 12. Once again, we're going to do the same things here. However, I'm not going to show it very detailed step by step. So that means here, for horizontal asymptotes, we're going to have that y equals to 0 is a horizontal asymptote. A vertical asymptote, we're going to have two of them again, x negative 3, and the other one is going to be at positive 4. And then the intercepts here are going to be the following: negative 4 and 0, which is our x-intercept, and then another one is 0 and negative 1/3, which is our y-intercept. Once again, we have a little conflict. Here we have a horizontal asymptote at y equals to 0. However, the x-intercept sits on y equals to 0. So there's one thing that people need to remember. It is a very common misconception of the horizontal asymptote, is that it's a boundary that a graph can cross. It's definitely true to a certain extent, especially when x approaches huge values, so plus minus infinity. However, the asymptote's purpose is to show the end behavior of the function. So that means if we have two asymptotes, the part of the graph which is between these two asymptotes never gets to approach infinitely large values of x. Hence, that part of the horizontal asymptote doesn't really apply to the function. So let's graph this here and I'll show you how it looks. Here, the graph is going to look like this. It's almost as if in the middle here we have a little parabola. Here, however, on the left-hand side is something that I want you to pay attention to. We have that part of the graph which is not between two asymptotes. However, it still crosses the horizontal asymptote at y equals to 0. But you can see that it happens not on the left-hand side, but rather on the right-hand side. That means that as this graph is going to continue, so x is going to go to infinitely negative values, so negative infinity, it's never going to cross the horizontal asymptote. However, As x approaches -3, so to the other side, it unfortunately can cross the horizontal asymptote because this is not an end behavior. Okay, now the last thing I want to show you today is that special case that I talked about. What happens when the numerator's polynomial's power is greater than the one in the denominator? Well, in this case, we won't have a horizontal asymptote, but rather something called an oblique asymptote. Another name for it is actually the slant asymptote. It's called slant because the asymptote is not a straight, like horizontal or vertical line. It is literally slanted. So let's take a look at an example. Here we have x squared minus 9 divided by x minus 4. Immediately, first, the vertical asymptote is definitely going to be at x equals to 4. Next, we won't have a horizontal asymptote, but since the power is greater in the upper part, we're going to have an oblique asymptote. Of course, in order to find it, we need to do polynomial division. In this case, it will most likely have a remainder, but that's not really a big deal. Polynomial division is basically like this. We take x squared plus 0x, since we don't have that, so we write 0x and minus 9. Why I write the 0, you will see later as the division goes on, it's going to be easier. Then we divide this by x minus 4. So in the upper part, first we do x. X times x, we get x squared, and then x times -4, we get minus 4x. We subtract this, x squared cancels out to 0, and here we have 0 minus minus 4x. So it becomes positive. Then we drag down the minus 9. So what happens here? Now we need to multiply by 4. So 4 times x, we get 4x, and then 4 times -4 minus 16. Subtract this again, the 4x is going to cancel out, and we will have a remainder that's positive, which is just 16 minus 9, which we get is 7. What this tells us is basically that x squared minus 9 can be expressed as x minus 4 times x plus 4, and then in the end we have to add that remainder 7. Of course, we can divide both sides by x minus 4 in order to get our rational function. So we get x squared minus 9 divided by x minus 4, which is equal to x plus 4 and then plus 7 divided by that x minus 4. Now, as x starts to approach positive or negative infinity, this part of our equation, so 7 divided by x minus 4, it is actually going to start approaching 0, while here in the front, it's going to be infinitely large values. So this tells us about the end behavior of our function, namely that the graph will get closer and closer to the line y equals to x plus 4. If we plot it, it's basically a linear function which has a slope of 1, and x plus 4 basically looks something like this. And then finally, finding the x and y intercepts can also kind of help you figure out that the graph is going to look something like this. So this video has had lots of twists and perhaps ambiguities. Don't worry if you don't understand it immediately. Of course, if you have questions, drop it in the comments, or you can write me an email, which is given in the description below. So that's going to be it for today. And the next time we're going to speak about radical functions and its properties. So I hope to see you there and have a nice day. Bye.